Okay, hello everyone. Let us continue the third part of today's class. Okay, we have said that taking action A of t plus 1 that maximizes the future Q value seen at the next state. So we take this action an of t plus 1 which is to maximize this Q value. Okay, so this is the meaning. The term Qt of Sn of t, An of t is the old learned value. Thus, the algorithm aims to minimizing the time difference TD error between the learned value and the current estimate value. The learning rate alpha. Okay, let me show you the alpha. Okay, here is alpha. Is set to alpha is greater than or equal to 0, and alpha is smaller than or equal to 1, which typically is set close to 0. Typically, Q-learning, where am I? Typically, Q-learning uses a sliding window to encode the recent history when the problem size is too large. While Q-learning performs well when dealing with small action and state spaces, it becomes impractical when the problem size increases, mainly for two reasons. 1. A stored lookup table of Q values for all possible state action pairs is required, which makes the storage complexity intolerable for large-scale problems. And 2. As the state space increases, many states are rarely visited, which significantly decreases performance. In recent years, DRL methods that combine a deep neural network with Q-learning, referred to as Deep Q Network (DQN), have shown great potential for overcoming these issues. Using DQN, the deep neural network maps from the partially observed state to an action, instead of storing a lookup table of Q values. Furthermore, large-scale models can be represented well by the deep neural network, so that the algorithm can preserve good performance for very large-scale models. Although convergence to the optimal solution of DRL is an open question, strong performance has been reported in various fields as compared to other approaches. A well-known algorithm was presented in DeepMind's recently published Nature paper. Okay, please see Mning et al. In 2015. Okay, we can see that Mning et al. And the title of the paper is Human Level Control Through Deep Reinforcement Learning, which is published in Nature in 2015. For teaching computers how to play Atari games directly from the on-screen pixels. Okay, what is Atari games? Let me show you some pictures. Okay, Atari games. Okay, like this. Okay, like this and like this. This we call 小精灵. Okay, do you remember? So, or like this, or like this, okay, or like this, etc. These are Atari's game. Okay. Atari games directly from the on-screen pixels. A survey of recent studies of DRL in other fields can be found in Lee, 2017. Okay, let us see Lee. Okay, the title of the paper is Deep Reinforcement Learning, an Overview. It is an archive preprint in 2017. Okay. We now overview DRL-based algorithms for DSA that have been developed very recently. We then discuss in detail the Deep Q-Learning for Spectrum Access DQSA algorithm that Naparstek and Cohen proposed in. First, Naparstek and Cohen in 2017. Okay, we can see that here. Naparstek and Cohen, and the paper title is Deep Multi-User Reinforcement Learning for Dynamic Spectrum Access in Multi-Channel Wireless Networks. In proceeding of the IEEE Global Communications Conference, GlobalCom. Okay. Available at Archive in 2017. Okay, next is Naparstek and Cohen in 2018. Sorry. Okay. Okay, Naparstek and Cohen. And the paper title is Deep Multi-User Reinforcement Learning for Distributed Dynamic Spectrum Access, which is published in IEEE Transactions on Wireless Communications 2018. And here is the DOI. Okay, you can click on this hyperlink. And the browser will show this paper, okay, and you can download the PDF here. Okay, please wait. Okay, like this. Okay, next in Wang et al. 2017. Okay. Wang et al. The paper title is Deep Reinforcement Learning for Dynamic Multi-Channel Access in International Conference on Computing, Networking and Communications, ICNC in 2017. Okay, and the second one is Wang et al. In 2018. Okay, Wang et al. And the paper title is Deep Reinforcement Learning for Dynamic Multi-Channel Access in Wireless Networks, which is published in IEEE Transactions on Cognitive Communications and Networking in 2018. The authors developed a spectrum sensing policy based on DRL for a single user that interacts with an external environment. The multi-user setting that we will discuss in detail in section 1.3.5. Okay, here, section 1.3.5. Okay, go back. However, is fundamentally different in environment dynamics network utility and algorithm design. In Chelita et al. 2017. Okay, let us see Chelita et al. Proactive Resource Management in LTEU Systems, a Deep Learning Perspective. This is an archive preprint in 2017. The authors studied a non-cooperative spectrum access problem for the case where multiple agents, that is, base stations in their model, compete for channels and try to predict the future system state. They use a long short-term memory LSTM layer with a reinforced algorithm in the algorithm design, and the neural network was trained at each agent. The idea is to let each agent to maximize its own utility, while the predicted state is used to reach a certain fair equilibrium point. From a better comparison point of view, it is worth mentioning here that the DQSN algorithm in section 1.3.5, okay, here, 1.3.5, as well as the problem setting are fundamentally different. First, in terms of the neural network architecture, DQSA uses LSTM with DQN, which is different from the DQN architecture used in Chelita et al. 2017. Okay, let us see Chelita et al. The paper title is Proactive Resource Management in LTEU Systems, a Deep Learning Perspective, which is an archive preprint published in 2017. Second, in DQSA, the DQN is trained for all users at a single unit. For example, multi-access edge computing, MEC, cloud, etc. This setting is more suitable to wireless networking applications implemented by chip SDRs. Okay, what is SDRs? It is the software-defined radios that only need to update their DQN weights by communicating with the central unit without implementing extensive training for each device. Examples are cognitive radio networks and the Internet of Things (IoT), which use a large number of chip SDRs for communications. Third, the DQSA setting allows training the DQN in both cooperative and non-cooperative settings, which leads to fundamentally different operating points depending on the desired objective. Furthermore, in Chelita et al. 2017, the hyperlink is not right. Okay, the focus was on matching channels to base stations, whereas the focus in DQSA is to share the limited spectrum among a large number of users. That is, matching might be infeasible. Other related work considered radio control and signal detection problems, in which a radio signal search environment based on gene reinforcement learning was developed. O'Shea and Clancy, 2016. Okay, let us see O'Shea and Clancy. And the paper title is Deep Reinforcement Learning Radio Control and Signal Detection with KERLYM, a GEM-RL agent. Okay, it is an archive preprint in 2016. Okay, to approximate the cost of search as opposed to asymptotically optimal search strategies. Okay, for example, Cohen and Zhao in 2015A. Okay, Cohen and Zhao, active hypothesis testing for anomaly detection in IEEE Transactions on Information Theory in 2015A. Okay, the second one is Cohen and Zhao in 2015B. Okay, Cohen and Zhao, asymptotically optimal anomaly detection via sequential testing, which is published in IEEE Transactions on Signal Processing in 2015B. Okay, and the third one is Huang et al. In 2018. Okay, we can see that Huang et al. The paper title is Active Anomaly Detection in Heterogeneous Processes, IEEE Transactions on Information Theory. And here is the DOI, and you can click on this hyperlink and wait for a moment, and you can download the PDF here. Okay, it is very convenient. Okay, like this. Okay, next page. Other surveys of recent developments and generalization of DRL to DSA can be found in Luang et al. 2018. Okay, let us see Luang et al. The paper title is Applications of Deep Reinforcement Learning in Communications and Networking, a survey. This is an archive preprint in 2018. And the second one is Mao et al. In 2018. Okay, we can see that Mao et al. And the paper title is Deep Learning for Intelligent Wireless Networks, a comprehensive survey, which is published in IEEE Communications Surveys and Tutorials in 2018. And the third is DeFellis et al. In 2018. Okay, we can see that DeFellis et al. Okay, Reinforcement Learning Based Spectrum Management for Cognitive Radio Networks, a literature review and case study, Handbook of Cognitive Radio in 2018. Okay, so this is a book chapter. Okay, other related works on the general topic of deep learning in mobile and wireless networking can be found in a recent comprehensive survey, Zhang et al. In 2018. Okay, we can see that Zhang et al. And the paper title is Deep Learning in Mobile and Wireless Networking, a Survey. This is an archive preprint in 2018, as well as the other chapters of this course. Okay. So now we are going to section 1.3.5, Deep Q Learning for Spectrum Access (DQSA) algorithm. In this subsection, we discuss in detail the DQSA algorithm that we proposed recently in Naparstek and Cohen, 2017. Okay, let us see. Naparstek and Cohen, and the paper title is Deep Multi-User Reinforcement Learning for Dynamic Spectrum Access in Multi-Channel Wireless Networks in proceeding of the IEEE Global Communications Conference, GlobalCon, okay, available at arXiv in 2017. Okay, next is Naparstek and Cohen in 2018. Okay, here Naparstek and Cohen. The paper title is Deep Multi-User Reinforcement Learning for Distributed Dynamic Spectrum Access, and is published in the journal IEEE Transactions on Wireless Communications in 2018. And here is the DOI. You can click on it, and you can find the PDF of this paper here. Okay, like this. Okay, based on deep multi-user reinforcement learning to solve equation 1.9. Okay, let us see. Okay, this is equation 1.9. We have seen this in today's class earlier. The DQSA algorithm applies for different complex settings and does not require online coordination or message exchange between users. We start by introducing the architecture of the DQN used in DQSA in section 1.3.5.1. Okay, is this section. Okay. The offline and online phases of the algorithm are described in section 1.3.5.2. Okay, this section. Okay, the training is done offline at a central unit, whereas the spectrum access is done online in a fully distributed manner after each user has updated its DQN. More details of the specific setting of the objective function and the design principles of the training phase can be found in Naparstek and Cohen 2018. Okay, we can see that this paper, we have already seen this before. Okay, next let us see section 1.3.5.1, architecture of the DQN used in the DQSA algorithm. We illustrate the architecture of the multi-user DQN used in the DQSA algorithm in Figure 1.4. Okay, it is 25 minutes. Let us take a break.